Hi everyone. So today we're going to finish up the course on by going through Thompson chapter 13. We're not going to cover the whole chapter. In fact, the sections we're going to cover, I'm going to skim through a lot of the calculation and just kind of give you the results as opposed to chugging through all the calculations and then being bogged down by a lot of algebra. So this chapter is going to cover the neutrino interaction, so which we have a hint of neutrino interacting with nucleons, neutrino interacting with quarks, right? And what's going to happen is that we're going to learn something new about neutrino, which is the fact that they oscillate and then why they oscillate. Okay, so in the standard model of physics, particle physics, right? We know that flavor, right, is a particular type of particle, right? So an up quark is a flavor, a charm quark is a flavor, top, tau, right? Muon neutrino is a flavor, okay? And when you have a flavor of a particular particle, right, its charge, its spin, its mass, right? There's properties to these particles that are fundamental to what they are, right? And well, guess what? Neutrino just like to break all these rules. Okay, what happened is that neutrino flavor does not actually define what the mass of the neutrino is. In fact, there are two separate ways to there are two separate sets of what's known as eigenstates, meaning, right, when you measure the flavor of a neutrino, it can come out as electron or muon or tau, but, right, the mass of the neutrino can come out in either mass 1, mass 2, mass 3. So an electron neutrino is actually a superposition of multiple masses, which is crazy. It doesn't make any sense, but neutrino does it, okay? This was actually discovered in 1998 at this experiment called Super Kamiokande. So it's in Japan, and the way that the detector works is that you just have a big tank of water. It actually says water in Japanese there, right? And this is what's known as the Cherenkov detector. We talk about Cherenkov detectors in the beginning of in chapter 1, but just to remind everyone. So what happened is that when you have a neutrino coming in and it strikes this water, so the water has a index of refraction, I think it's like 1.25 or something like that, right? So therefore, the speed of light inside that particular medium is slower than 3 times 10 to the 8. And therefore, when a neutrino comes in, and let's say you have an interaction here, like maybe this one, neutrino come in, interacts with the electron cloud around it, around a particular atom, right? And it knocks out one of these electrons. Now, this is a charged particle passing through this. Is an electron charged particle passing through this water now. And if that particle is going faster than the speed of light, what happens is that it'll just make these cones of light that comes out. Okay, and this is due to basically how the water gets polarized and depolarized, basically at the speed of light, and this cone is created because this wave of circular light, they're coming out also at the speed of light. Okay. Another way that a neutrino can interact, it can interact with the nucleus. We did some calculations with this last time, right, in chapter 12, where you have a neutrino comes in, right, it exchanges a W with some nucleon, okay, that nucleon breaks up into other stuff, right, but the thing that's interesting is maybe a muon neutrino, right, I mean, even though they're dealing with electron neutrinos here, maybe a muon comes out, and this is another charged particle that comes out, right, at the speed of light, well, faster than the speed of light in that particular medium, and therefore you can actually make this Cherenkov light cone also. Okay, so that's the idea. And so the way that this detector works is that it needs fairly high energy neutrinos, right? Because you need to knock out this electron or this muon in order for it, or convert a muon into convert a neutrino into a muon, right? And it has to have enough energy so that it's traveling at faster than the speed of light in that particular medium to make this Cherenkov light. But the cool thing about this is that the Cherenkov cone, right, basically points exactly the direction that your charged particle is going, and therefore most likely the neutrino is going to be going in the same direction, okay, just from conservation of momentum. Okay, so it's a very good measurements of direction of the neutrino, and it requires high energy, but once you have that high energy, you can also measure this energy also. Okay, so how does this detector measure neutrino oscillation? Well, how do we figure that out? So if you were on Earth, okay, I think most of us are on Earth, okay, and this detector is placed on Earth. I don't know, is this yeah, I guess this is Japan. It's like a rotated version of Asia or something like that, okay? The Earth is constantly being bombarded in every direction with cosmic rays, okay? And these cosmic rays makes, pions, and then these pions decay into muons, right? And then when these muon decays, they decay into muon neutrinos, okay? So you basically have a source of muon neutrino coming in all directions all around you, okay? And the location, right, of a detector is not going to be at the center of the planet, right now the core, you locate it on the surface. So a neutrino coming from, let's say, this direction will only travel maybe like tens of kilometers, right, before hitting your detector, while a neutrino passing through here will actually pass straight through the planet, right, because the interaction cross-section is so small, okay, and then hit your detector, but it would have traveled basically the diameter, diameter of the planet, okay? So in this way, right, if you have a neutrino coming straight down, it travels a very short distance. If you have a neutrino that's coming straight up, it actually travels through the Earth, so it has a very long distance. So you actually have a measurement of neutrino that has traveled different distance, okay? And this is the plot they see, okay? This was completely unexpected, okay? So what's being plotted on the x-axis here is the distance that the neutrino travels. So, because if you know which direction, right, if the neutrino comes straight out of the ground, right, you know it traveled through the entire planet. If the neutrino came in from like maybe this direction, right, then you know it traveled, maybe like a quarter of the planet. So you actually know from the direction how far that neutrino has traveled in order to reach your detector. Okay, so that allows you to measure the length, and then basically the size of the cone of the Cherenkov light tells you the energy. So you actually have both of these variables. And then if you plot this, okay, put this on the x-axis, and then basically measure, okay, the amount of neutrinos per, the rate of neutrino that you're getting, what you get is you basically have this kind of downslope here, right? And it has this kind of like a wave behavior, right? It's like we're going to see what this, oscillation is, right? Okay. Okay, so that's actually the first evidence from 1998 where people are saying, wait, these neutrinos are A, not massless, B, they actually decay, right? There's fewer neutrino that has to pass through the Earth than those that just came straight down from the atmosphere, right? You would think they'll be exactly the same because, right, the neutrino would just pass through the entire planet and hit the detector no matter which direction they came from. Okay, so something wonky's going on. In fact, I think they were awarded the Nobel Prize 2014. Okay, all right. So there are more evidence for this neutrino oscillation. Okay. This is another experiment called CAMLAN. Okay, it's also in Japan, and Japan is just kind of a neat place for this because Japan has a lot of fission detector. Okay, so make sure I'm saying fission instead of fusion. Okay, they have a lot of them. Okay, what does fission do? It makes neutrinos. Okay, so you have sources of neutrino, right? Let's say you have a little power plant here. The neutrino come in all directions, but CAMLAN is located here. So if CAMLAN detects a neutrino coming from this direction, right, it knows it has traveled this distance in order to get there. So once again, you have a way to measure the distance that the neutrino has traveled, right? And you know the neutrino's energy by measuring the size of these Cherenkov cones. Now you can also plot basically, right, the what's known as the survival probabilities, because a lot of fission interaction produces electron neutrinos only. It doesn't produce muon neutrinos or tau neutrinos. So we know that all these fission reactors are actually producing electron neutrinos. Okay, and what you see is that you have this kind of up and down, right? And now as a function of basically L0 divided by the energy of, in this case, anti-electron neutrinos. Okay, so now we'll start to see, okay, so there's something going on that's, either that looks like a sine or a cosine wave. Okay, so how does this happen? Okay, why does having neutrino mass that are different from each other, right, and having them being different, having the mass eigenstate and the flavor eigenstate being separate, right, how does that create oscillation? Okay, and the answer is, of course, what we're going to do is quantum mechanics. Okay, so if we start with the Hamiltonian, okay, right, the Hamiltonian governs how the state, the wave function, or whatever object we're talking about, how does it evolve with time, right? Okay, and this wave function, right, can be written as some positional dependence times some time dependence. Okay, so stuff that we talked about. I think this was in chapter 2, right, when we were starting to talk about quantum mechanics. All this stuff, it's the same as before. We haven't done anything different yet. Okay, so the flavor eigenstate are denoted as nu e, nu mu, nu tau. The mass eigenstates are denoted nu1, nu2, nu3. Okay, just so we have two different distinguishable ways to denote them. We actually don't know if actually one corresponds to the electron or one actually corresponds to the tau. Okay, if one does correspond to the electron, this is known as the normal hierarchy. But if nu1 actually corresponds to the tau, it actually shows that it's known as the inverted hierarchy. We actually don't even know this right now. Okay, and there are ongoing experiments trying to measure this right now. Okay. So let's say you have a W plus, right? And a W plus, right, decays into a positron. Right? You have a positron coming up, and then you have a neutrino coming out. Okay, this neutrino could be, right, if the flavor eigenstate is exactly the same as the mass eigenstate, 100% of the time, this will be nu e, right? But it's not. Okay, so sometimes it comes out as nu1, sometimes it comes out as nu2, sometimes it comes out as nu3. Okay, so when a W plus decays into a positron plus a neutrino, we actually don't even know what type of neutrino we're talking about. Okay, so the electron basically couples to all three different neutrino mass eigenstates. Okay, so the electron, right, is supposed to decay into an electron neutrino. Okay, but that electron neutrino is actually a linear combination of three different masses. Okay, that's really, really weird, right? Because the thing we've been talking about so far, when we know is if it's an up quark, we know the mass of the up quark, okay, with some uncertainty, right? If it's a W boson, we know the mass of the W boson. We know, if you have a pion, even proton, right? We know the mass of a proton to 50 digits or something like that, right? Okay. So if we were to repeat this with basically, instead of decaying into a positron, it decays into a mu plus or tau instead, right? Oops, these are going to be plus, right? Okay, what we're going to see is that, right, the electron neutrino is actually a linear combination of all three possible mass eigenstates of the neutrinos through these matrix elements. One is called UE1. Basically, it tells you how much electron neutrino is contributing to the one eigenstate of the one neutrino, okay, or how much the electron neutrino is actually being turned into neutrino 2, or how much the electron neutrino is being turned into neutrino 3, right? And these are different mass eigenstates. Okay. So in the interaction vertex, the stuff we've been drawing up here, right? The wave function, right, is actually, right, turns the electron neutrino, which is this is, you're starting off with an electron neutrino, but that has the probability of being it has a contribution, right, from UE1, right, being in the mass eigenstate 1, or being in the mass eigenstate 2, or being in the mass eigenstate 3. So basically the wave function is actually a linear combination of all three different mass eigenstates. Okay, so how did we deal with this before? Well, we actually did it wrong the first time. Okay, so in chapter 12, we assumed that the weak vertex described the flavor eigenstates, right? Which is not true anymore. Okay, because in this little diagram, right, we always show that electron neutrino always turns into a electron, right? Or a tau neutrino always turns into a tau. Or if you go backward, right, an electron always couples to the electron neutrino. This is actually not true, right? The way we write this, right, this top part here, right, we write this as a current where you have a electron, right? You have the gamma and mu, and then you have the V minus A stuff, right? That's the thing that projects out the left-handed particles, and then you have the electron coming out, the neutrino coming in. Right, you have this weak coupling constant, right? This is wrong. Okay, we can't do this because, right, this electron actually couples to not to electron neutrino. It actually couples to nu1 plus nu2 plus nu3, right, with some constant in front of them. Okay, and these constants are this matrix, right, up here, known as the mixing matrix. Okay. And so the way we should have actually written this is that you should have, instead of writing this electron neutrino, you should have written it with these matrix elements, U alpha K, Vk, where K is, goes from 1, 2, 3, indicating which mass eigenstate we're talking about. Okay. So you can see this turns into a fairly complicated mathematical problem that already was complicated to begin with, right? So when you're drawing Feynman diagrams with this neutrino mixing to begin with, what you need to do is now, instead of drawing just this weak coupling constant, this vertex here, this vertex, right, is going to be proportional to these matrix elements that we're talking about up here, right? Whatever these numbers are, okay? And these are actually, in general, can be complex numbers, okay? So let's do the simplest possible way to deal with this. And even with the simplest possible way, there's already some pretty complicated calculations, so I'm going to skip a lot of that just to get to some of the results that we can use. Okay. What we're going to do is we're going to do a simple example with just 2 flavor mixing. So we know there's 3 neutrinos, but I just want to show you guys how you can actually do some predictions on with 2 flavors, and therefore show you how the 3 flavor version will just be you're doing the same thing, but just the algebra is exponentially longer because, right, you have to deal with 3 different flavors and mass eigenstates of neutrinos. Okay, so first, let's define these 2 mass eigenstates, right? So nu1 is the 1 eigenstate, and then nu2 is the 2 eigenstate. Okay, and these eigenstate will evolve with time. Okay, right? So the time evolution of these mass eigenstate, it's just whatever this initial value is. Basically, this is like t equal to 0, right? Times this wave function, right? This e to the I px minus et. Okay. In fact, you can actually just write this as p2.x, right? Where this is basically this is the 4 vectors. Okay, to shorten this. I think this should have had 2 in front here. Oh, sorry, nu2 and then nu1 here. Okay. So, since we're dealing with just electrons and muon, the 2 flavor, and not dealing with tau, we're just kind of ignoring the tau for now. Okay, we can parameterize that matrix that we saw before, right, with a single angle, and this single angle is going to be cosine along the diagonal, and then basically sine and negative sine on the off diagonal. Okay. In fact, we can do, maybe we'll do this as a little homework problem. You can invert this matrix and show that if you invert this matrix, then you just basically move the -1. The negative sign moves from the bottom to the top. Okay, so suppose that t equal to 0 and at some distance equal to 0, right? You created an electron neutrino. Okay, so therefore the initial wave function, right, is a pure electron neutrino, but an electron neutrino in this 2 flavor case is actually a combination of both the mass 1 and mass 2 eigenstates. Okay, and then the amplitude for that, right, is basically going to be cosine and sine by just doing this matrix multiplication here, right? Okay. As time goes on, right, the state's going to evolve, it's going to change. Okay, and the time evolution of that is just by sticking on this e to the I px, right? Where this is the 4 vector dot product, right? Okay, you do the same thing for the second mass eigenstate, right? V2. Okay. So therefore, at some time t later and some distance L from the starting point, right? Remember that P dot x is basically E times t minus P times x, right? And then since x is the distance that, is traveled, right? Then that's just the L distance there. Okay, let's just, I think usually we just assume this traveling along like, the z-axis or something like that. Okay. So with that, what we can do is we can define this as a phi, right? Where phi indicates basically a phase angle, okay, depending on what the mass, what the energy and the momentum of these particles are, okay? And since their masses are different, right, the ratio of energy and momentum will be slightly different between them, and therefore they would actually have a different phase, and therefore we actually have to have a phi1 and a phi2 for the 2 different mass eigenstates. Okay. And now there's a little bit of algebra. Okay. And what we're going to do is we're going to use the inverted matrix here. Okay. And basically substitute in, right, V1, right, is a linear combination of nu E and nu mu, right? So we're going to use that and substitute in this, okay? So that basically, let me just use a highlighter instead. Make it a little bit more clear what we're trying to substitute in. So just substituting in this, okay? That's what that is. Okay, nu1 is a combination of electron and muon neutrinos. Okay, nu2 is also a combination of electron and muon neutrinos. Okay, but instead of having a negative sign, you have a positive sign between them, right? All right, so now, right, we multiply all these, we multiply all these cosines together, right? Now you have a cosine square, right? And then we factor out, we collect the terms that has nu e's together, right? And then all the terms with nu mu together, okay? And then you have this factored out, and then you have basically e to the minus I phi 1 cosine square, e to the minus I phi 2 sine square, right? And that's your electron, neutrino amplitude. Okay, you have something very similar for the muon neutrino amplitude. Okay. In fact, what you can do is factor out e to the I phi 1 completely. When you do this, what happens is that, right, you're basically, since these are in the exponential, when you factor this out, you're basically going to be subtracting minus phi 1, and therefore it makes it actually positive. When you factor this out, you're going to pick up this additional, you're going to have this extra phase difference between the two neutrino mass eigenstates. Okay. Similarly, when you factor out the same thing here, you also pick up this phase difference. Okay. All right. So the important thing is that, right, this phase difference is due to the fact that E1 and E2 are different from each other for the two different mass eigenstate, right? Because if they have exactly the same masses, their energy will be exactly the same relative to their momentum, and therefore E1 minus E2 will be 0, P1 minus P2 will be 0, and there'll be no oscillation whatsoever. Okay? So the masses of the neutrino has to be different just from noticing that they do oscillate. Okay. Okay. And if this delta phi is 0, right, then let's see, right, delta phi is 0. You get a 0 here, and then you get a 0 here. Oh, you don't get a 0, sorry. Yeah, e to the 0 is 1. You get a 1 here, right? 1 minus 1 gives you a 0, and therefore this whole new part is just 0, right? So an electron neutrino always stays the same as an electron neutrino if this delta phi is 0, right? Which it is not, because these neutrino actually have different masses. Okay. I'm going to skip a lot of the steps to get to this point. So if you want to calculate the probabilities, you basically just kind of do the bracket version of this. But what happened is that what you end up with is that if you calculate the probabilities of a electron neutrino turning into a muon neutrino, the results basically turns out to be the sine square 2 times theta, just because of a bunch of trig identities. Okay. And then times sine square of delta phi 1, 2 divided by 2. Okay? Okay. So there's two parameters that specify how these neutrino oscillates. Okay? The first one is the angle theta. The other one is actually this delta phi 1, 2. Okay? Delta phi 1, 2, right, remember, is the difference between the two phases. And these two phases is basically the difference of the energy of the two masses and the difference in the 3 momentum. So these are 3 momentum, right, magnitudes, okay? Since the 2 mass eigenstate actually propagates forward together, right? So you know, you have a neutrino, you start off with a electron neutrino, right? It's moving forward, but in reality, it's actually a combination of, you know, mass 1, mass 2, and they're moving together, right? Right. They're moving together as basically a wave packet that is actually spreading out little by little over time, okay? But what we can argue is that, well, the momentum between them will be the same because, right, the spreading is kind of small for now, okay, at some short distance, let's say. And Thomson actually say, yeah, this is not true at all. Since we're dealing with this toy model anyway, which is also not true, which is dealing with 2 neutrino flavors, just as an example. So we're just going to take this as a way to just get some result that is pretty decent also. Okay, so if we assume that, you know, this term goes to 0, right? E1 and E2, we can calculate what E1 and E2 is, and that's basically going to turn, you know, just using E1 equals to E1 squared equals to P1 squared plus M squared, right? Or this is the 3 vector, okay? Okay. And then since we're defining these magnitudes to be the same, M1, M2, right? We're making these the same anyway. So these just both turn into just P squared, right? And which is what is plugged in over here, okay? You solve this for E1, you can actually parameterize this as P parentheses 1 plus. So if you multiply this in, this will turn into P squared, right? M1's square minus over P2 square, all square rooted, because you have to square root both sides to solve for E1 and E2, right? And so this phase difference between them is going to be equal to the difference between these 2 momenta, which is assumed to be the same, okay? And then basically the mass difference between them, okay? Right? So to write this 1 plus M1 square P2 P square to the 1/2 power, you do a binomial expansion and you only take the first term. So if you haven't seen this, I suggest you really look it up because it's very useful to get a good approximation. So 1 plus something to the 1/2 power is the same thing as 1 plus 1/2 to that something. So that's where that 1/2 went. Okay, so this is the first approximation. Okay, so if you plug those in, so I'm even going to write this out, right? So delta phi 1, 2 equals to P. We can factor out the P. The T goes out here. Okay. And then you have 1 plus M1 square over 2P square, right? And then that's this first part here. And then minus 1, right? Plus, minus, right? Parentheses 1 plus M2 square 2P square, okay? Right? Times time, oh, well, already broke down the time here, okay? Right, P times T. So the ones actually subtract each other out. And then the 2 actually, you can factor out 1 over 2 times P squared, right? Did he make a mistake that this is actually L? Yeah, let me see. Okay. Okay, so one of the factors of P cancel out. Then you have M1 squared minus M2 squared here. Okay. Okay, so delta phi12 should be this times time instead. Okay. 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 So replacing the momentum of the neutrino as basically the energy of the neutrino, because the mass of these neutrinos are so small, right? In this case, this condition holds. We can actually convert basically this phase into this, where it's the difference between the two mass square, right? Then this time basically gets converted from momentum. The momentum gets converted into energy, and this time gets converted into the length that the in natural units, how far the thing traveled. Okay, so this is all in natural units, but oftentimes it's not very convenient to measure things in natural units because no one really measures things in inverse GeVs. Okay, and what you actually convert to, let's say, unnatural units, okay, where you can actually do these measurements. You can convert this length basically to kilometers instead, and this delta M is going to be in electron volt square because this is such a small mass. The the energy of the neutrino is going to be measured in GeV because the energy is high enough so that you have GeV amount of energy. And then when you do this conversion here, you end up with this factor of 1.27 from converting from natural units to unnatural units. Okay. All right. And now this is where at the point you can actually make some plots because, right, you have the sine square 2 theta here, which is actually this theta, right, is a constant, right? It's just a number. Okay, so this actually just kind of gives you some amplitude here, right? But then you have this sine square function that depends on how far away you are from your source, your neutrino source, how far the neutrino actually traveled. What is the energy of the neutrino, and also the mass difference square of those neutrinos. Okay, so this is where this plot down here shows you. So this is the probability of an electron neutrino turning into a muon neutrino, okay, as a function of L in kilometers, okay, and this is per a 1 GeV energy neutrinos, and then we're assuming that the mass is going to be the mass square difference is 0.002 eV squared, so it's a very small mass difference. Okay, and this amplitude here is assumed to be 0.08. Okay, so in this toy model, right, we can see that the probability of an initially, right, the electron neutrino is an electron neutrino, but as time goes on, it turns into a muon neutrino. Okay, and then so if you catch it right here, it actually has an 80% chance of being a muon neutrino, but then it oscillates back down at about 1,200 meters, 1,200 kilometers away, right? It disappears, and then so it keeps oscillating up and down, up and down, up and down. Okay, if you take 1 minus that, right? 1 minus the probability of the neutrino turning into a muon neutrino, okay, you get the probability of the electron neutrino not turning into the muon neutrino. So you get the probability of the neutrino staying the same, and that's what this dashed line is showing. Okay, it's just 1 minus that. Okay, notice that the sine square 2 theta tells you the amplitude, right? This has how big this this oscillation is. Okay, the wavelength of this oscillation, right? You can actually also calculate it, right? The wavelength, right, is just the pi times the energy of the neutrino divided by 1.27 from up here, and the mass splitting between the two different mass eigenstates of neutrinos. Okay. Whew. So we'll have you guys make a couple of plots and just so you can see this nice simple toy model of 2 flavored neutrinos. Okay. Next, I'm going to go through the 3 flavor version, and I'm going to skip 99% of the math. Okay. Just but then we're just going to get to some interesting results so that we can utilize it. Okay. So as you can see, right, I even with the 2 neutrino flavor, I skip a lot of math steps already. Okay. With 3 flavors, you can imagine this. The math is much, much, much more complicated. In fact, I think Thompson, had like 10 pages of math on this. So if you're really interested, and you want to do theoretical calculations with neutrinos, I really, really suggest you read through that this section, 13.5, which he dives into detail on how to calculate these 3 neutrino oscillations. But I'm going to outline what he does. Okay, so instead of a 2 neutrino, 2 masses, right now we're dealing with 3 different mass eigenstates and then 3 different flavor eigenstates, right? And the coupling, right, the probability of one being the other, right, is all parameterized with these U matrix. This is actually known as the PMNS matrix. I'm not even going to try to say all these names all in a row. So these are people who figure out how to mathematically deal with these matrices, parameterize how neutrino actually oscillates. Okay, so this is a 3x3 matrix, and each of these are complex numbers, right? But these matrices has to be unitary, right? Because if you don't have unitarity, what happens is that if you apply this matrix twice, right, then if it's, let's say, bigger than 1, then what happens is that you don't preserve probability anymore. Okay, so therefore, right, it has to satisfy this condition that, right, the matrix itself, so this is the U matrix, right, and this is U dagger, okay, they have to multiply to 1, right? This is essentially writing that U dagger equals to the identity matrix. Okay. What that does is that it constrains 1, 2, 3, 4, right? To constrain the parameters, these parameters down, because you're forcing these things to be equal to 1, forcing these things equal to 0, and stuff like that. And so we actually really only have 4 independent parameters. Okay. And this is where, these guys, PMNS, right, separated out these parameters so that you can actually kind of think about them more physically as opposed to trying to deal with these 9 parameters all at once. So what they did is they separate out. I'm going to look at, so what they're going to do is they're going to separate this one matrix into 3 simpler matrices. Okay, why would you deal with 3 matrices? Because these 3 matrices are simpler. This one, right, is the 2 neutrino flavor, right, mass splitting version already. The stuff we just dealt with up top, right, in the previous section, right. You might note this cosine, sine, sine, cosine, right. So there's one parameter here, right, theta. This angle theta 1, 2, right, is the parameter. Oops, yeah, I should actually write what this is, right? Cosine C1, 2 equals to cosine theta 1, 2. Okay, right. So and then so on with sines and stuff like that. Okay, right. So the parameter for this whole matrix, depends on this one angle. Okay. Over here on the left-hand side, you have the same thing, but then with the tau muon instead. Okay, so here you have theta 2, 3 as the parameter. Okay, in between, sandwiched between them, you have theta 1, 3, and then you also have this delta, which is often denoted as delta CP. So this is actually what's known as the CP violating phase. We're not going to talk about that too much in this class, but in the future, when you see, when people talk about the neutrino CP violating phase, this is the angle they're talking about here, right? This one. Okay. All right. If you multiply all this stuff together, you get this giant long equation. But, right, don't be afraid of this. There's actually 4 angles in this whole matrix. Okay, and that's determined completely how neutrino oscillates into each other. Okay. All right. So these angle here, right, we're going to further define them as this difference. Remember, it was difference in the phase angle that matters between them, right? And this is going to define what the phase difference between 1 and 2, the phase difference between 2 and 3, the phase difference between 1 and 3, and then this delta 1, we're going to keep that separate, okay? We can actually measure this by basically measuring the neutrino oscillation wavelengths, right? Because remember, when we go back up to the 2 flavor version, go up here, right? If we know this wavelength, right, we can actually figure out what this delta m square is. If we know the L, we know the energy, we can actually figure out what delta m square is, right? Right. So people actually have done these experiments, and we found that the mass square difference between 2 and 1, right, is about 7.6 times 10 to the negative 5 eV. Very, 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 very small number. Okay. Okay. I mean, the mass difference square between 3 and 2, whatever they're, for these eigenstates, is bigger, right? 2.3 times 10 to the minus 3 eV. Still a super crazy small number, but, right, that allows us to figure out what the mass difference is, okay, by measuring basically the wavelengths of those neutrino oscillation as a function of different L's, different E, right? Okay. And we also found that the mixing angle, delta 1, 2, delta 2, 3, delta 1, 3, right? Basically it's 35, 45, and 10. Okay. So delta 1, 3 has the smallest angle. Okay. Okay. Right. So note that we can always only measure the difference in the mass, not the mass directly. Okay, I'm going to talk about how we actually can measure in the future, be able to measure the mass of the neutrino directly, but that's a different type of experiment, not this type of oscillation experiment. Okay. Okay. So for example, in the CAMLAN experiment, right? Remember, this is the one where you have a neutrino detector in middle Japan. You have multiple different nuclear reactors shooting neutrinos into CAMLAN, right? So, in fact, these nuclear reactor tends to make anti-neutrinos because of the electrons that's being produced, and that creates an anti-electron neutrino. Okay, so the probability for a electron anti-neutrino to stay a anti-neutrino, if we go through all the math and stuff like that, is going to be approximately, okay, which is where things are, which is where we're going to do with a couple of homework problems here. Okay, it's going to be cosine to the 4th power theta 1, 3. Okay, so remember, this is just a constant. That doesn't have to deal with the wavelength and stuff like that. 1 minus sine square times 2 theta 1, 2. So remember, this is the amplitude of the oscillation. Okay, and this here is what actually determines basically the period. Either you can call it the period or you can call it the wavelength because you're actually plotting this as a function of distance, so it actually is a wavelength. Okay. So what you can do is by figuring out what this wavelength is. Okay. So this whole period. Well, actually, before we even do this, okay, I'm going to have you guys do this in the homework, but I'm just going to get you guys started. Right. The amplitude of this oscillation, right? It's from like 0.25 to 0.9, right? So therefore, right, the amplitude, right, is 0.65, right? It's just 0.9 minus 0.25, right? That's the amplitude. That's going to equal to this, right? Okay. All right. I'm not going to go do the exact thing, but hopefully you guys will figure it out. Okay. The wavelength, right? We can do. We probably want to pick this middle part where there's a little bit less noise, right? Where it comes from the oscillate from the peak to peak, right? That tells you exactly what the wavelength is, right? This wavelength, right? So maybe this is like 35 kilometers, and this is at about 80. So the wavelength is actually 80 minus 35 kilometers. So that's actually 45 kilometers if I can do my math, right? Right. So that's the wavelength, and that's actually going to tell you what delta M12 is. Well, delta M12 square is, okay? Right? Because you know exactly what L is, you have to know exactly what E is, right? So the wavelength is actually determined by that. Okay, so I'll have you guys do that in the homework. Oh, by the way, this is known as short baseline, meaning the distance that the neutrino travels is something on the order of 100 kilometers. Okay. There are also these things called long baseline. One of them is called MINOS. The U.S. is actually building another one that's going to shoot neutrinos, I think, about 2,000 kilometers. This one only shoots it about 735 kilometers from Chicago to Minnesota. Okay, they're actually building one that's going to shoot it from Chicago to South Dakota right now. Okay, and they're actually working on that. Okay, this is going to produce muon neutrinos because the way that they make the beam of neutrinos is by basically smashing protons onto a target, and those protons create pions, and those pions decay, as you know from last chapter, mostly into muons and not into electrons, right? And these muons decay into neutrinos. Okay, sorry, the pions, when they decay into neutrino, it produces muon neutrinos at the same time. Okay, so so in this experiment, okay, the probability, the survival probability, right, if you estimate what that is, okay, it's going to be 1 minus A, which is the amplitude of the oscillation, sine square times this delta M square of 3,2 times the length divided by 4 times the energy, of course, once again, okay. And so this data set is a little bit less clean, okay? So you want to look at this right-hand side and basically figure out what this wavelength is, but you only get half the wavelength, okay? Okay. Oh, by the way, the reason that you don't, this is not a function of L over E anymore is because, right, here, right, you only have one L. There's literally only one L you can use. You don't get another L, okay? Where in CAMLAN, right, you get different L's, where at the at MINOS, you only get one L, okay? And I'll have you guys figure out what the wavelength of this is, and therefore you can actually figure out what delta M32 is, okay? All right. The last thing I'm going to talk to you guys about is basically how you actually can measure neutrino masses. So from just astronomical data, we know that the neutrinos, the sum of all their masses all together, right, has to be less than an eV, okay? In oscillation experiments, we know that, right, delta M12 is the smaller one, and then delta M32 is the bigger one. Okay, both very small numbers still. Okay, what that means is that we can actually visually see this where, right, delta M12 meaning, oh, well, if the neutrino 1 and neutrino 2, right, is the lower of the two masses, right, this will be how they will look like, where mass 3, whatever that happens to be, is going to be way up here, right, because the difference here is much bigger. Okay, but we could have a case, right, because we only have the absolute value of delta M32. Okay, therefore, right, we have to, well, delta M32 could have what's known as an inverted hierarchy, where the third neutrino mass eigenstate is actually the lowest mass, and then 1 and 2, those are the two higher mass. Okay, so this is known as the normal hierarchy, and this is the inverted mass hierarchy. Okay, and we don't know what this is yet. Okay, so there are experiments trying to measure this. One of them is called Lecture13. This is a really cool experiment where basically they have a tank of tritium, and the idea of tritium is that it decays. Let me get this picture. Okay, it decays into a neutrino, an electron, and a helium-3. Okay, we don't really care about the helium-3. Okay, so what you do here is that you measure the electron that's coming out. Okay. Okay. Why do we measure the electron that's coming out? Okay. So when the electron comes out, oops, you can actually have it bounce back and forth and then interact with other things. And what you do is you measure the energy and the momentum of this electron extremely well. Okay. Why would you care about this? Okay. The reason you care about this is that basically the energy spectrum, meaning how much neutrino, how much energy that comes from the electron gets, because basically when this decay, there's a certain amount of energy that's being shared, right? And this is being shared between the helium-3, the electron, and the neutrino. Okay, that is a fixed amount, no matter what the decay, no matter what happens. Okay, you get that amount of pot energy. So basically, if you can figure out how much energy is being given to the electron, you can do this thing called a endpoint measurement, where if the mass of the neutrino is exactly 0, you end up with this blue line, okay, where it actually just kind of curves and it goes away. Okay. But if the mass of the neutrino, let's say it's 1 eV, which is much bigger than anything, it shouldn't be that big, right? Because the sum of them has to add up to 1. So therefore, each of the individual component has to be less than 1. But you would get this red line here, where it will end, right? Basically, the difference here will be 1 eV, okay? Because that 1 eV went into making the mass of the neutrino instead of being converted into kinetic energy. Okay, and this is how Lecture13 is trying to measure the mass of the electron neutrino by just taking tons and tons and trillions of events in order to measure this very, very precisely. Okay, in fact, I have a paper that came out last year. What they found is that, well, the mass of the electron, so this neutrino is only the electron neutrinos because the decay only happens with the electrons, is less than 0.8 eV. Okay, not a very good constraint yet, but they've only been taking data for a couple of years, so as more and more data comes, they can actually figure out, constraint what is the mass of the electron neutrino, and then eventually, let me go back up. You're going to hit this point where, right, so this is the mass square, okay? Eventually, what will happen is that you basically hit these point where you're on the order of 10 to the minus 2 eV on the constraint of the mass of the electron neutrino. And at that point, you can actually figure out, oh, well, if that's the case, it has to be this guy up here or this guy up here, okay? So you actually know whether or not the electron neutrino is mostly V3 or mostly V1 by that point, okay? So hopefully, I don't know how long this lecture went, but this is my last one. So, and it's on neutrino, of course. So, and neutrino is the best. Well, it's the best mystery that is surrounding us right now. So, hopefully, you guys enjoy this overly long lecture video. Oh, yeah, it's over an hour long now. So, I will end this and then write up some problems for this. Okay.